A useful feature of the Cartesian plane is that we can talk about distance between 2 points that live on the plane. We do have a formula called the distance formula. The distance d between 2 points x1, comma y1 and x2, comma y2 is given by d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Now this formula looks pretty complicated. I'm going to share with you where it comes from. You don't have to memorize this unless you want to, because it is kind of just the result of something that you should be pretty familiar with. The thing that you should be familiar with is called the Pythagorean theorem. Remember that the Pythagorean theorem only applies to what are called right triangles. So if we drew a picture of a right triangle, where we've got one right angle, and then we have this hypotenuse here. Here how we represent that right angle with a square in the corner. Then there's a special relationship that exists between the lengths of all of the three sides. Side 1, side 2, and then side 3, which is that special side called the hypotenuse. So we've got two legs and a hypotenuse. Let's label these. How about A, B, and C? The relationship that exists between these three sides always is if you add the squares of each of the legs, so a squared plus b squared, this will always be equal to the square of the hypotenuse. So this is what Pythagoras, another philosopher and mathematician from before Descartes' time, discovered about these kinds of shapes. Now, applying the Pythagorean theorem to the coordinate system or the Cartesian plane that we just reviewed, let's see. We have 2 points x1, comma y1 and x2, comma y2. So we're just going to plot those. I don't know what they'll look like here. Here we have, oops, I should label my axes, x-axis, y-axis. And maybe this first point here, the one on the left, we'll say that that's x1, comma y1. And then the other point here, we'll label this as x2, comma y2. And what we're looking for is the distance between these points. So we're calling that lowercase d. Now, if we had grids here, like on a graph paper or something, that might be a little easier for us to maybe count the length of the boxes that this diagonal goes through. But in general, when you have the diagonal of something in a rectangle, it's kind of hard to count. It's not going to be a just nice, thing that we can count from the graph. So we do need this formula. Now, if we kind of make this d distance the hypotenuse of a triangle and just kind of in our minds or even actually on our graph, sketch the legs of the triangle that would have this as its hypotenuse. That makes it easier for us because then what we can do is use the number line grid or our count our boxes here to figure out how long is this leg, and then we can use this nice horizontal line to figure out how long is that by either counting on the axis or maybe figuring out what that length is another way. So our points here, maybe we can put these on the axes. So here this will be x1, that length there for this point here. Our x coordinate's x1, so it's on the x-axis, and the y coordinate of that point is y1, so right here we've got y1. For our other point, which is over here on the x-axis, that number there or that length will be out to x2, and then the y coordinate is y2, so the height of that point will be y2. So if we're going to figure out what is the length of this part, this leg, well, if we just go over on the axis, on the y-axis, that's the same length here. And if we, had some numbers here, we would just take the higher number and then subtract the lower number. So the length of the vertical leg here is going to be y2 minus y1. The same thing will be true on the horizontal leg. So if we just want this length, then that's the same as this distance here, and that's just the higher number minus the lower number. So the length here on the horizontal leg will be x2 minus x1. Now applying the Pythagorean theorem to this triangle will give us that if we square doesn't matter the order, but if we square this bottom leg first, then we will have x2 minus x1, parentheses squared. Then we'll add the square of the other leg, parentheses y2 minus y1 squared. That has to be equal to the hypotenuse squared, which we're calling d. And if we just solve this for d by taking the square root of both sides, then that actually gives us the distance formula. So if we solve for d, we will get the square root of x2 minus x1 plus squared plus y2 minus y1 squared, and that is equal to d. Now let's practice using this formula. In example 1, let's plot the points -2, 5 and 6, -3, and then find the distance between them. I would always suggest that you try to draw a picture anytime that you can, and also use that alongside any formulas that you might be using. It can help you get a better, deeper understanding of what's going on. So let's plot these points. Let's make a nice set of axes and make sure that we label them. So we've got the x-axis and the y-axis. We need to have some scale on each axis. I'm just going to look at the points here. My highest x goes up to 6 and my highest y goes up to 5. So I'm just going to kind of keep that in mind when I make my scale. I'm just going to go out to 6 everywhere. If you don't want to label, every single tick mark, that's okay, as long as you label one of them. This indicates to everyone, hopefully, that, each one of these is 1 if I went out to 6 and labeled that 6. Okay, so the points that we're looking at, -2, 5, that's to -2 on the x-axis, and then up to 5 on the y-axis. So that point lives right there. Then the other point that we have is 6, -3. So we're going to go out to 6 on the x-axis and then down 3 on the y-axis. And so that's going to live right here. So here's our second point, and I'll label that as well, 6, -3. Now we're looking to find the distance between these 2 points. So if we connected them with a straight line, what we are looking for is this length d. There are 2 ways that you can go about this. You could sketch in a nice right triangle, just like we did when we were figuring out why the distance formula is what it is. Then you could actually count the lengths of the legs by utilizing the number line. So we've got a nice horizontal line, how many, how long is this? Then we've got a nice vertical line here on the y-axis. We can figure out how long that is. So doing that first, and then we can try it the other way as well. Let's count how far we have on the horizontal axis or on the horizontal leg. So this length here, again, we can just count. So I start here. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that length here is 8. Then on the vertical leg, the length that we have from here to here, we can count as well. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So that length is also 8. Now using the Pythagorean theorem, we would say that 8 squared plus 8 squared equals d squared. And then we would figure out what d is. So 8 squared is 64. So we have 64 plus 64 equals d squared. And if we add 64 and 64, we will get 128. And so we need to find d, so let's take the square root of both sides. If we take the square root of 128, I don't believe that that is a perfect square, so it's probably the best idea to just leave it in its nice, exact value here and just say that it is equal to radical 128. That's all right to leave it like this, but we could also see if there's a perfect square hiding inside of 128. And that should be kind of clear that there is, because it's actually two 64s, right? We do 2 times 64 or add 64 to itself, and we get 128. And 64 is 8 squared. So we can write this as inside 2 times 64, and then that 64, which is a perfect square, can come outside of the radical as an 8. And a maybe better answer for this, or a most simplified form, would be 8 radical 2. Now let's just see how we might use this in the distance formula, and also that we get the same thing. So all we have to do is make sure that we label our points correctly. So the negative 2 comma 5, I'm going to call that one x1 comma y1. And then the 6 comma negative 3, I'm going to call that x2 comma y2. It doesn't matter which order that you do this in, you will get the same result. So if I write down my formula with my numbers in there, x2 was 6 and x1 was negative 2. So we'll have 6 minus parentheses negative 2 squared. Then we will add y2 minus y1 squared. y2 is negative 3 and y1 was 5. So we'll have negative 3 minus 5 squared. Now what we want to do is try to simplify what's underneath the radical first. We want to get in like a number inside of there. So we'll do 6 minus negative 2. We'll end up adding 2 to 6, so that's 8. Then we've got negative 3 minus 5. That is negative 8. Now if we square 8, of course, we get 64. And if we square negative 8, we also get 64. And so here we'll have the square root of 128, which we can simplify again to 8 radical 2. So either way that you like, whether you like the picture and figuring out that way, or maybe you like the formula, it doesn't matter to me which way that you do a problem like this, but they should both make sense. In example 2, we are looking at finding an x value where we know the distance, but we're looking for a certain point that is a distance away from another point. So we'd like to find x such that the distance between the points 1, comma 0 and x, comma negative 4 is 5. So let's try to draw a picture of this just to reason through like what's going on here instead of just mindlessly using the formula. I'm going to draw my x-axis and my y-axis, and I'm going to label them. And I only need to go maybe to 5 out on each axis because I've got, a negative 4 there. So I'll just kind of make sure I label everything out to 5 and negative 5. Okay, so our point we have here is 1, comma 0. So let's plot that one. 1, comma 0 is right here. Then the other point we have is x, comma negative 4. Now, how do we plot that? We're looking actually for the x coordinate. But we do know that its y coordinate is negative 4. So that means it's going to live somewhere where the y coordinate here is down at negative 4. And our job is going to be to figure out, where should this be in the x direction? Should it be down here, right below that original point? Should it be maybe over here? Should it be over here? Should it be way out here? I mean, at some point, the distance is going to be too far, right? We're looking for this to be 5. And at some point here, maybe it'll be just right. And there's going to be some symmetry, so that we'll get actually maybe 2 points because we can have a distance of 5 in maybe 2 directions. Okay, so again, we're looking for a point that lies, down here on this dashed line, and we want to figure out where that should be. Okay, so plugging into our distance formula, now we actually have that the distance d is 5. So we're going to have 5 equal to the square root. Okay, now let's label our x1, y1 here. So I'm going to say x1 is 1 and y1 is 0. And then x2 will be x, and then y2 will be negative 4. So let's substitute these into the formula here. So x2 is x, and x1 is 1. So we have x minus 1, and then we square that. Then we add y2 minus y1, so that'll be negative 4 minus 0, and then we square that. Now let's simplify what's inside of the radical. X minus 1 squared, we can leave that for now. Then we've got negative 4 minus 0, that's negative 4, and then we'll square that, so we'll have plus 16. Now we're looking to solve this for x. This x is like kind of bundled up inside of this radical. We could just get rid of the radical by squaring both sides. So I'm going to do that. So I'm going to do both sides squared here. So we get rid of the square root and we can access that x underneath. When we square the left-hand side, we'll get 25. And here we're looking to solve this for x. Now let's go further and try to isolate the x. So I'm going to do minus 16 on both sides. 25 minus 16 will give us 9. And we'll have 9 equals x minus 1 whole thing squared. Now to undo this square here, what we can do is take the square root. Now when we apply the square root to something, we have to make sure that we take the plus and the minus version of whatever number we're square rooting. Okay, so we need to basically get two different equations here. We're going to have one where the left-hand side will become positive 3. Oh, no more square. And then we'll have another one where the left-hand side will become negative 3. Okay, again, when we apply the square root to a number, we will get the positive version and the negative version, because if you square 3, you get 9, and if you square negative 3, you also get 9. So we need to make sure that we consider both possibilities. Now, if we solve this for x, we'll just add 1 to both sides in this equation here, so we'll get 4 equals x. And we'll do that on the other equation as well, so we'll get negative 2 equals x. All right, so here are two values. Now let's go back to our picture and see if that makes sense. So let's plot the points here that we found. So the first one, here would be 4 comma negative 4. So that's 1, 2, 3, 4, negative 4. So that's right here. Okay, so that's that point. And then our other point there was negative 2 comma negative 4. So we're looking here, negative 2 comma negative 4. So it'll be right around here. Okay, now we do have this nice symmetry here, and the distance, the length between each point, it's kind of hard to tell, but it should be equal to 5.